All right, class, so this is an explanation video for how to solve for a simple Ka problem, so a simple weak acid, just, pretty basic here. And this is from the day 4 handout. So let's just get into it. The first question here says calculate the pH of a 0.056 molar HCN solution, and then it gives us a Ka. It says Ka for HCN is 4.9 times 10 to the minus 10th. So the first thing that you'd be thinking about or whatever would just be that HCN is a weak acid, right? That's the first thing that I would say. And we should be able to write out on equilibrium for this of HCN dissociates into H plus CN minus. This is a weak acid. This is telling us it's a weak acid. If we're given a Ka, this is the first thing that we should be thinking about and writing out. And then we're asking for the pH. So the pH, that's going to be the concentration of H plus. That's what we're looking for. So that'll be my equilibrium concentration here. And then my initial concentration is going to be 0.056 molar HCN. So I'm going to say that I have a essentially 0 H plus. Now I'm writing essentially 0 H plus there because there will be some H plus from the autoionization of water, which when we have really, really low concentrations, we may need to sort of consider. But for most intents and purposes, this is always going to be 0. So I'm going to write approximately 0 just to keep that in the back of my mind though. Plus x on the right with the minus x on the left. And then I'm going to have 0.056 minus x, and x for my equilibrium concentrations. So the next thing that I need to do is figure out, well, if this is my Ka, 4.9 times 10 to the minus 10th, then that should equal x times x, or x squared, over 0.056 minus x. And we get to this stage here. So at this stage here, you can use the quadratic formula to solve for x. That is totally valid. But there's this sort of shortcut or trick that we can use, and we can use the sort of assumption that this bottom part will essentially be equal to 0.056. If I know that this x value should be really, really small, and in this case I know that that x value should be really, really small, because this Ka value is so small, that suggests this reaction is not going to go very far to the right. There'll be very few products. So this x value here is probably going to be really, really small, and that makes it so that this assumption of saying, well, this minus x term on that 0.056, it's probably negligible. So if I do that, it becomes really easy for us to solve for x. X in this case is going to equal 5.24 times 10 to the minus 6th. If you solve this with the quadratic formula, you would find that you get essentially exactly the same answer. So if you're doubting me on that or whatever, go ahead and just check, right? So just go and plug this in, see if you get any difference. Another way that we can check, another quick check, is that we can take 0.056 and we can subtract that x value. We can say, what if I did subtract this? What do I end up getting? And you end up getting the same exact number, right? So that equals 0.056. So that should tell us that's a good assumption. The other way to do the check, which we'll do on the second problem, is to take your x value and then divide that, or find what percentage of the initial that is. So take this value divided by 0.056, multiply that by 100. If it's 5% or lower, then you're good to go. And if you actually calculate that for this problem, it's like really, really low. It's below 1% by far. So this is a good assumption for this problem here. So if this is my x value, that's going to equal my concentration of H plus, right? So x value will be my concentration of H plus at equilibrium. And then I can just go ahead and find my pH. pH should equal 5.28. So that should be the pH for that problem there. Okay, so let's do the next one. The next one's a little bit more involved. We will have to use the quadratic formula, as you'll see in just a second. So calculate the pH of a 0.056 molar HF. Again, I know that this is going to be an equilibrium. I know that my products will be H plus the conjugate base. That's what a Ka, always will be. A Ka will always be a weak acid dissociating into H plus and the conjugate base. That's sort of the definition of Ka. And I'm given my value here times 10 to the minus 4th. And my initial is going to be the same, 0.056, 0 and 0, or essentially 0, minus x plus x plus x. We're shifting to the right. 0.056 minus x. So this should all be exactly the same. Now 7.1 times 10 to the minus fourth equals x times x over 0.056 minus x. Again, looking very, very similar so far. So now we're gonna see what happens if I make that same assumption. I'm gonna assume that that x is negligible, and we can solve for that x, and we get a value of 0.0063. So now if I do my little check, I notice that it does play a role. It is going to change that value a little bit. And if I calculate the percentage, if I find 0.0063 divided by my initial, and I multiply that by 100, that equals 11.2%. So this tells me that it's probably not a good assumption. So this is telling us not okay assumption. So from here, this is really telling us, well, we actually do need to solve the quadratic, or we should. So if I solve the quadratic formula, then the way that would look, if I multiply everything out, minus 7.1 times 10 to the minus fourth times x equals x squared. And then I can simplify this, so I get 0 equals x squared plus 7.1 times 10 to the minus fourth x minus 3.98 times 10 to the minus fifth. So my a, b, and c values, a is 1, b is this value here, c is this value here. Solve the quadratic for x. I get minus 0.00667. Obviously that cannot be the right x value because we cannot have a negative concentration, or 0.00596. So this is going to be my valid x value. And you notice that they are a little bit different, right? 0.0059, 0.0063. They're close, but they are a little bit different. So I can use this. This is going to equal my concentration of H+. And then my pH for this will equal 2.22. So that's really the best answer. If you do calculate the pH over here, you get a pH of 2.20. So they are pretty close, right? Pretty close. But technically this is going to be better here, and we sort of need to keep that in mind. All right.